Hello, my name is Brianna, and today I want to talk about human evolution. Now, when we think about things that set us apart from other animals or other primates, we often think about things like our massive brain and the ability to use that brain to create tools, manipulate fire, communicate with one another using abstract language. We could also think about things like bipedal locomotion. But something that I find that doesn't come to people's minds as often or as immediately is hairlessness. Even though if you look at a chimpanzee and then you look at us, it's kind of obvious that we have a lot less hair than they do. Now, that's not to say that we don't have hair. We do. We have hair on our scalp, our eyebrows, our eyelashes, our face, our chest, our genitals, our legs, our arms. Um, there is some variation. Hair can be sexually dimorphic in how it presents itself on a certain individual, but there is a big difference between a chimpanzee and a human. There's no question about that. The hairiest male will not compare to a chimpanzee. And this is interesting because we still have the same number of hair follicles that chimpanzees do. It's just that our hair is a lot thinner, it's a lot shorter, and it's a lot more non-pigmented than a chimpanzee's. At least in regards to areas of our body that don't appear very hairy. So like the back of our ears, you can kind of feel that fuzz maybe. Those are called vellus hairs, and those are those very thin, reduced hairs I was talking about that are present on a chimpanzee but have been very reduced in humans. And this is weird because hair can do a lot for us. It can provide protection against the sun, against biting insects, against the environment. Like if you run into a branch, it protects you against getting scratched. Hair can keep us warm. It can keep us cool. It can do a lot of things for us. So the fact that we don't have it is a little odd. And I think it's kind of exemplified by the fact that genes that code for properties of the skin are some of the most different between the human and chimpanzee genomes. Our skin is a lot more scuff resistant and water resistant than a chimpanzee's skin is. So something happened in our evolution for us to have lost our hair and buffed up our skin to compensate for that loss. And that's what I want to talk about today. Now, there are three hypotheses that we're going to look at that kind of try and attempt to explain hairlessness. The first hypothesis that we're going to look at today is the ectoparasite hypothesis, which suggests that hair reduction evolved to prevent parasitic infection. Now, there are lots of different variations of this hypothesis, so we're going to be looking at one specific one today, and that is the one proposed by Brown in 2021. He proposes that ticks were the primary culprit behind the loss of our hair. He suggests, if you look down here at this flowchart, that our last common ancestor with chimpanzees was kind of gibbon-like and lived in forests. And 5 to 8 million years ago, when there was forest fragmentation occurring, this last common ancestor traveled between these forest fragments on the ground, which had them run into a lot of ticks. And because ticks can harbor a lot of disease, that led to the selection for hair loss because it was more advantageous because you're able to see hair better. And this kind of led us to having our obligate bipedal locomotive lifestyle. So he suggests this occurred around 5 to 8 million years ago, which is relatively early in human evolution. The next hypothesis we're going to be looking at is the thermoregulatory hypothesis. Now, proponents of this hypothesis suggest that hair reduction evolved to allow for more efficient thermoregulation. If our hominin ancestors were utilizing the savanna during the heat of the day, they would need a way to cool off because it was just so hot. So they adapted by really exaggerating our ability to sweat. Now, sweating is mainly carried out by our eccrine glands. As you can see here, this little blue gland that's coiled up here, which secretes sweat onto our skin. And the evaporation of that sweat off of our skin transfers energy in the form of heat from our skin to the environment and cools us off entirely. And this is especially efficient if we don't have any hair in the way. So we reduced the amount of hair that we had, and that allowed us to evaporate this sweat directly off of our skin, which cooled off our blood and was able to more efficiently cool down our entire core body temperature. Proponents of this theory suggest that this occurred around 2 million years ago. And then we have the bestiary hypothesis. Now, again, there's a lot of variations of this hypothesis, so we're just going to be looking at the one proposed by Kuchlin in 1985. And he believes that hair reduction evolved following the invention of clothing because it provided the ability to keep ourselves warm when it was cold out. The idea being that we weren't able to lose our hair because it was disadvantageous because it was too cold. So when we were able to actually keep ourselves warm, we were able to lose our hair. He suggests this has occurred around 500,000 years ago, which is relatively late in our evolutionary history. Now, there are 3 ways that we can evaluate all of these hypotheses that we just talked about. The first of which being with lice. Now, there are 3 different types of lice that parasitize humans, 2 of which belonging to the genus Pediculus, and those being the head louse and the body louse, and then one belonging to the genus Pithyrus, being the pubic or crab louse. And these lice have a very interesting evolutionary history. This is kind of why I started thinking about this question, because I read some papers and I was like, wow, this is really interesting. So we have 13 million years ago, if you look at this phylogenetic tree here, we have a duplication event, the emergence of the pediculus lineage in the solid line and the Petherius lineage in the dotted line. And around 7.5 million years ago, we can see this split of the pediculus lineage, which became extinct, and the gorilla lineage shortly after, but continues on. And we can see it split again here, this pediculus lineage, in around 6 million years ago, going down to Homo and going down to Pan, co-speciating with the last common ancestor between chimpanzees and humans. More interestingly, if we continue on with the Petherius lineage, which became extinct in the Pan-Homo lineage, we can see that there was a crossover event from gorilla to the Homo lineage around 3 to 4 million years ago. Now, the reason this could have implications for hair loss is because the Petherius pubis, which is parasitizes human pubic hair, wouldn't have had a home if humans didn't have pubic hair. And a lot of people think that pubic hair emerged after we lost our hair or in tandem with the loss of all of the rest of our body hair. So around 3 to 4 million years ago, it's reasonable to suggest we had pubic hair and thus didn't have a lot of body hair left. So if we look at about 5.61 to 1.84 million years ago being the 95% confidence interval that Reed et al. Came up with, we can predict that around that time range is when hair loss occurred, with an average about 3.32 million years. We can also look at MC1R data, and MC1R is the genetic locus that's responsible for coding melanin, which is the protein involved in skin and hair coloration. And the reason this is so helpful is because our ancestors, like this chimpanzee down here, was likely light-skinned under all their fur. And once they lost it, they needed something else that could protect them against the sun. And the answer to that question was melanin. As you can see in this map here, individuals that are native to areas of the world that have high levels of UV radiation, like Africa, where our ancestors evolved, they need that melanin to protect themselves against the harsh rays of the sun. So if we were utilizing the savanna and we didn't have hair, we needed melanin. And so we can look at the genetic history of MC1R and determine that hair loss occurred at least 1.2 million years ago. We can also look at physiological data. Now, as I've said, we have this ability to sweat, and we sweat well, and it allows us to do these very, very vigorous exercises like long distance running in the heat. And so if we can look and see these we see evidence of our ancestors doing these activities, then we can presume that they likely had the ability to sweat and thus likely didn't have hair, because it would be more efficient to sweat if they didn't have hair. So we're going to look at some of these anatomical features, mainly focusing on the ones in this box. So we can see long legs here with the emergence of Homo erectus. We can see these expanded joint surfaces as compared to Australopithecus. You can see these are much wider in this picture than as seen in the Australopithecine. We also have narrow and elongated waists as opposed to this wide pelvis and this funnel-shaped thorax. We also have greater structural independence of the shoulder girdle and head. It is kind of seen in the Australopithecus by these shrugged shoulders. That kind of indicates there is a lot of muscle attachments there that would have been advantageous for things like climbing, but less so for long distance running. And we also can see wide shoulders in Homo erectus and less so in Australopithecus. And again, we can see these in Homo sapiens as well. So by Homo, but really with Homo erectus, is when we can see these anatomical features that are consistent with activities like long distance running really emerge. Homo erectus is often considered to be the first hominin with modern body proportions. They kind of emerged around 2 million years ago. So when did we lose our hair? It's a complicated question to answer, even with all the stuff we just talked about, but the thermoregulatory hypothesis is most likely, and we're going to kind of go through all of them together. So the ectoparasite hypothesis predicted hair loss to occur around 5 to 8 million years ago. It's a little too early for the physiological data, but it does coincide with the upper limit of lice data, as you can see here. The predicted in the orange does overlap a little bit with the actual. And it does line up with the MC1R data. It's at least 1.2 million years old. We could also look at the vestigial hypothesis, which suggested that hair loss would have occurred around 500,000 years ago. And it's just too late for all forms of the data that we looked at, the physiological, the lice, and the MC1R. As you can see, there is no overlap in the lice data. The vestigial hypothesis, as proposed by Kuchlin in 1985, is not likely at all. We could also look at the thermoregulatory hypothesis, which suggests that hair loss occurred around 2 million years ago. And this lines up with all lines of evidence that we looked at. There is some overlap in the lower limit of the lice data. It lines up with the MC1R data, and it lines up with the physiological data very well. So it does appear with everything that we looked at today that the thermoregulatory hypothesis is the most likely hypothesis in explaining why we lost our hair. And this can have interesting implications on the evolution of our species. And it kind of goes to show that something that we might not see as central to our identity, like we see big brains as central to our identity, that is hair loss, it can still have super amazing and insanely consequential impacts on the evolution of our species. So thank you very much for listening. I very much look forward to the conference poster session on Friday. Thank you for listening.